Okay, the main theme throughout this class is when you have a symmetry that lets you solve something. Very often it's having the thing that defines the time motion, that is the Hamiltonian and the evolution operators, being written in terms of symmetry operators. And this is no exception here. This is a review of something that you've had in every quantum mechanics class would have this one-dimensional harmonic oscillator. But I want to make sure that we see right away from the very beginning that what we're doing here is writing a Hamiltonian in terms of some group algebra operators. And so that's what these AA daggers are, and we have to get those. That's the first step. Okay, and then of course the algebra of them is rather interesting. So we're going to spend a good deal of time doing the bookkeeping of that algebra again. You already know a lot of this, but it's worth seeing it again in the context of a symmetry. And then the next lecture will be with 2, so we'll be taking up the U2 problem. And of course at that point we'll realize this goes on forever, U3, U4, U5, and so forth. By the time you get to U4, it's probably not true that you're having euphoria, but you should. Okay, so the basic idea here, and we have 2 screens here, so we'll make use of them, and then some simulations later on. But the basic idea of factoring this is, I think, really important to know, because that is the symmetry. So I'm just making a kind of a joke that I make every time when I teach this, and some of you have already seen this joke, so you don't have to laugh. But the idea is, question, how do you convert a classical Hamiltonian for this oscillator, this is just a one-dimensional oscillator, into a quantum harmonic oscillator problem? And what I say is, you simply get out one of these markers, a thick pen, and rewrite the equation using a thick pen, okay? E squared x, you make them thick, okay? Well, that's a good start, all right? But it really bothers a lot of people is, well, okay, so I've got a thick pen. How do I solve this Hamiltonian? Okay. Well, what you do is you buy a thicker pen. Okay. And what you're going to do is you're going to factor this thing with this. Okay. That's the whole idea of this business here. Factor that. That's the real deal here. And the idea of writing this as a polynomial, write it as a reduced factor form. Okay. Well, there's a couple of flies in this ointment here. The problem with that is that these x's and p's here, and that's the thing, is you have to figure out what are those x's and p's. A couple of clever ways to show that the P is a differential operator. That's something you'll learn right away. And that's something that we haven't covered yet. That goes to the relativity stuff that shows how quantum mechanics and relativity are the same. And the process of redoing Hamilton-Jacobi analysis of the phase and the Hamiltonian, we can arrive at this in a very solid way. But you've all seen this, so you will take it for granted. So the basic idea is, while you're using this thick pen, you'd better write it in a way so that one of the factorings has the minus sign on the right and the other one has it on the left. This is to make it symmetric, because this thing has this symmetry that's associated with P and X, but we're going to make it into a combination of X and P, very much like how we made the position on the left plus the position on the right into a projection operator. Well, these things are not projection operators yet, but they're the beginnings of it. They're the skeletons of it. So that's really what we're doing here. And then recall this little thing, and that's, of course, an important thing to do. XP minus PX. The question is, these don't commute, but well, what's the difference between them not commuting or not commuting? So in very small letters here I've written that these two operators, X and P, don't quite commute. Okay? Almost. They almost commute. Okay? Question is, how much is the difference between commuting and not commuting? Okay? That's the real gather here. In any case, if you just go ahead and do the x partial of x and then partial x, subtract the two of them from each other, you get something that is essentially zero. This thing right here is what you get. Minus h bar, okay? So it only misses commuting by 0.000, and I got to go 34 times, right? In order to tell you how big that is. Okay, so I think that's something you should be aware of, and I'm going to make that point a couple of times during the lecture as we go ahead and do the usual things of obtaining first eigenstates of an oscillator, and then what's really magical about the harmonic oscillator are the coherent states. That's when you get to go back and see where classical mechanics comes from, given quantum mechanics.
Dr. Harter, when quantum mechanics was formulated, was this commutation relation put by hand?
The operator quantum mechanics really had a hard time getting born. And I say born as in Max Born. Okay, Max Born is one of the originators, but really it was Schrodinger. Okay. But before Max Born, we have the Einstein, Bohr, Kramers, etc. I can't think of all of the names, where they would simply use the classical phase and quantize that. And they said, you have to do that because that's what a wave will do. It will, by boundary conditions, be forced into quantization. So all of the problems were being solved without any of this wave mechanics. Schrodinger and Max Born and a few others are responsible for getting that going.
Because in all the textbooks on quantum mechanics, we assume that this one holds good, x and p, the commutator equals IH bar, and then we derive everything from that. So I was just wondering, was it an educated guess? Like, did people...
Well, your first phrase was all the quantum mechanics books. Where do most of the quantum mechanics books come from? They come from Fermi's notes, who came from Oppenheimer. Then they got stuck in, I can't think of the first book that actually put it in a hard book, hardcover. Most of the time it was notes floating around. And they, you know, once people start doing something, everybody just follows. It wasn't until Feynman wrote his book that you really had a different way of looking at the quantum mechanics, which we're essentially following here, or trying to. Okay, and plus we have a few extra things to add. So anyway, this is the situation here where you have this commutation relation, which is practically zero. It's practically zero until you're talking about x's and b's that are practically zero. That's what quantum mechanics is really all about. Okay, so what we have to do is do the algebra of the symmetry that this system has. And basically you can see what the symmetry is. And I can factor this thing so easily because both the p and the x are just squared. You replace p with x and x with p, it doesn't change the Hamiltonian at all in these units, right? And I'm taking those funny units that we took to make our U2 Hamiltonian. We're going to come back to the ABCD matrix, right? That is a two-state system. So we're going to be coming back to that on Wednesday, a couple of days from now. But let's get the first dimension out of the way and do everything we can with it, and that's what we're going to take on today. So we need to figure out how you get the so-called vacuum state. What is that really? What is the first excited state? And basically what we're doing here is making an algebraic structure that gives you Planck's axioms, E equal n h bar omega. That's what's going to happen. Okay? We're just going through this fancy group algebra to get that. So we're trying to mirror quantum mechanics, the nature of quantum mechanics, Mother Nature, using all of this algebraic bookkeeping. So we'll end up just using x and p, and we may at some point call h bar 1 and take the frequency just to be 1 to make things really simple. Doing a lot of algebra, that would certainly be nice. But most of the time, that's what we'll be dealing with. We'll be dealing with the big X's and the big P's that are written with really thick pens. Okay? So I'll put those away. It's all up here on the screen. And for a while, I'll keep all of the parameters that have to do with an actual mass oscillating in a potential. And our animations will basically be showing that. But be aware that that is just a sort of a classical non-relativistic oscillator. There's another one that's going to be obeying these equations, which is a relativistic harmonic oscillator, electromagnetic wave in a cavity. Okay, so be aware that that is a relativistic oscillator. And that's the one that you should look at if you want to get a real feeling for the connection between relativity and quantum mechanics. Okay, so here comes this big old mess of putting the A and the A dagger in a commutator. And you figure, well, I already know the commutation of x and p, what do I need to do this for? Well, this is going to give you a commutation that's really simple, and you want it to be simple because remember the thing that I said when we said that one of the bugbears of symmetry is you've got to do the products of the algebraic parts of the symmetry, you see. So here's where we build that product, except the product is a commutator. So what we do is go ahead and just put these two right next to each other, and so I end up here with an expression that gives me a minus I over h bar times the commutator of x and p. So that was a pretty simple commutation relation, but this one is even simpler. A dagger is 1. Okay? That's easy to remember. Now some of these things are up on the wall. I have to have them up there because I can't remember that, but you have probably a better memory than I do. So one thing to put in your permanent core of memory is A dagger equal 1. And we'll generalize that for more dimensions, but that's all we need today. Okay? So just using this commutation relation, which is hi times 1, that's pretty simple. Just remember the p's on the right, otherwise you get a minus sign. And this one you have the dagger on the right, where we don't like to have it. We like to get the creation operators on the left, but we'll get to that later on. So this is an expression, that's another way to write it. A dagger is equal to a dagger A plus 1. So we're going to build everything just on this. This is everything that's going to happen today is going to be the result of this simple product relation of the group U1. It's very seldom expressed that way, but that's what it is. And it's the symmetry group of one phasor. Okay, and the Hamiltonian can be very easily written in terms of, well, it's already been pretty nicely written, x squared plus ip, or x plus ip, x minus ip, but this is what it is. This is the symmetrized form of that, and of course we can turn that around because a dagger A is a dagger A. I'm sorry, this guy right here comes out of that guy. So very quickly we get an expression that you should probably have memorized as well. And that is that the Hamiltonian is essentially just this. But here's this crazy thing that we get. We get one of these for each dimension of an oscillator. So this is essentially the form we're going to have for our two-dimensional, three-dimensional, four-dimensional, so on oscillators. We'll just keep adding more of these darn halves. For electromagnetism, which has two polarizations, we're going to add two one-halves. So the electromagnetic two-dimensional oscillator associated with just the polarization of a beam, okay, has got no one-half. And it's a sum over two, x and y, okay, combinations. All right, so that's, of course, for the next lecture, but I just wanted to warn you that that's what. This thing called the zero-point motion, we get to understand what that is. I think that's a key thing. So anyway, we got a lot of bookkeeping to do here, and I want to make sure that I do it as carefully as possible just to get this. But the idea of this is that there is something called the ground state, that is a state below which you cannot fall, so somehow we have to get that worked in to our mathematics, our logic here, and have that as our result. That is, have this right here, whatever you get just from this, regardless of what this gives you, and we assume, we're going to assume that this thing right here gives you 0 when you multiply the Hamiltonian by it. That is essentially the axiom of this particular derivation of the spectrum that we're going to get. Now we can do the H on the ket, or you can do it on the bra. Supposedly either one of those is going to give you this result, the energy equal h bar over 2. And of course I can put it together so that it's the expectation value of the Hamiltonian. The idea is that the action, this is the real axiom right here, is that the action of A on this thing called the ground state, the zero state, the vacuum state, gives nothing. Literally an operator 0. Okay, from either side. Okay, so giving this thing right here, this creation operator, that doesn't necessarily give 0. We have to figure out what that is. You see, that's the idea here. So what does the Hamiltonian do when it runs into a creation operator acting on this? Well, it gives you 3 A's. There are 2 of them with daggers hanging up in the air. And then, of course, there's this h bar over 2 with that thing, and that's not necessarily 0. So we have to account for that expression. Go ahead and rewrite this thing so that it comes out to be an A dagger of the 0 plus, and what we're seeing right here is another 0, and then we've got another one of these down there, okay? So we end up with something like this. We end up that we have some sort of eigenvalue, we'll just call it E1 for now, which is h bar omega plus the vacuum, okay? Now, at this point we wonder, is this really going to go? This thing right here, this is going to be a state that we can actually have? Well, yeah, it is, but we would also like to know what was the wave function for the state that we started with here that had this axiom that you can't get anything from an operator A on the 0. So what we can do with both of these equations is rewrite this thing in such a way that we can actually figure out what this x A0, that's what we're going to be calling the wave function of this nothing equation right here. So this is an equation that we can solve. It's the starting point of any oscillator discussion. So I'm going to go ahead and put the P operator in the coordinate form that we're used to. And the X operator in, well, it's just X. And then there's this unknown X zero product, product, which we're calling psi zero here. And that leads to an equation that's first order in both the psi and the coordinate x. Okay, so this is something that's just going to turn into a d psi over x equals psi and a constant. And that's going to be an exponential. Okay, so we're going to be integrating that ratio, getting a logarithm, which gives us this. So that's the famous Gaussian wave function for the vacuum state of the oscillator. Okay, that's kind of neat. It's this thing. Okay, and it's what's going on the screen down at the end there. Okay. Now, once again, as I harp like an old lady about all of the quantum mechanics books that came from the notes of Fermi, and then Oppenheimer used it, and I'm still trying to think of the textbook that came out of the Berkeley lectures with Oppenheimer. But of course, they never had a computer. They never could really show what the wave function looked like in time. But that's what it looks like. It's got a real and imaginary part all the time. It just sits there underneath an absolutely rigid, solid, never moves Gaussian, which is the absolute magnitude of this wave function here. Okay, so that's what we're dealing with, is that this thing is going to be oscillating at this frequency right here. And what is that frequency? That's the frequency where this particular energy actually cuts the parabola. That's the 0-point motion. Now remember when we talked about the difference between the infinite square well with the prism and twice that which had no walls, which was the Bohr rotor, right? The Bohr rotor had no 0-point motion, right? Because it was free to go around. There wasn't anything to reflect it. And you had two kinds of eigenfunctions once you got a non-zero k. If you're 0 k plus or minus 0 is the same, but if you have 1 plus or minus 1, that's two different wave functions. The prism didn't have that, right? It just had a wave function that looked pretty much like this one. It was a sine wave that was going up and down, and there was none of this wave going into the region where the difference between potential and energy becomes imaginary, that is, an evanescent tail on either side of this thing is what we have here. With this infinite square well, there was no tail. It was infinitely small. Now, a finite square well has a tail and a 0-point motion that varies in a complicated way. This one is so simple. Yeah.
The real and imaginary part of the wave function oscillate at the frequency of the oscillator, right? So
yes, this frequency right here,
right,
is exactly equal to, in units of h bar, 1/2. 1 unit is right here. That's a frequency unit of 1, which we're going to jump up to in a minute as we get the state number 1. But right now we're just looking at state number 0, okay, which isn't quite 0 in terms of its frequency. It's 1/2 in units of h bar omega. And that's what's being shown here. Okay? So we've got this 0-point energy right here that just corresponds to the fact that this thing can't be confined to that little dot at the bottom. Does that make sense? Or as much sense as anything in quantum mechanics is supposed to make?
Can you repeat that statement?
I don't know if I can. Somebody else want to try? The basic idea here is that, like the prism with finite walls, or like the Bohr rotor, there is a lowest energy point. Now the Bohr rotor, remember, the lowest energy was right at the 0, the bottom of the a potential that wasn't there, right? It was just kinetics. No potential. Now, prism, put a prism up and you get some value for the 0 point energy. It's in the order of this. But this one is very quantifiable. The energy for this one is, as we've already seen, exactly 1/2 of h bar omega. 1/2 of the jump that we're going to make to the next eigenstate, number 1, which is going to be up about there. This is how high? Twice that's a here. So if I go from there to there, that's where my next energy level, and you can see that actually marked off on the screen down there, above the phasor that is oscillating on this.
So as you keep moving higher on the energy ladder, your the real and imaginary part will oscillate much more rapidly.
They will each time gain a frequency of h bar omega. I mean, they'll gain a frequency of omega, whatever that omega value is, each time. They'll gain an energy of h bar omega. Energy and frequency, same thing, except for a scale factor that makes the connection between the quantum mechanical optical classical units, MKS units. So, what you should realize that there are classical turning points. So, I drive an energy through this parabola right there. It hits the parabola at certain points where the potential plus kinetic is 0. So,
those
I'm
inflection
sorry, the
points.
potential is 0. Potential minus the energy value that we have here, which is 1/2 omega.
Are those also the inflection points of psi 0?
You bet. Absolutely. Thanks for noticing that. When we cross the boundary here, the wave function goes from having a positive, if you call that positive, you have to turn your head upside down to call that positive, that's really negative curvature, and then it becomes positive curvature on this side. In other words, the second derivative of the wave function is changing sign right there. And the second derivative is exactly the energy minus potential, or potential minus the energy. Okay, does that make sense? Yeah. And we'll see that with all the wave functions we derive here. Okay. So, here's where we make the connection between that weird algebra of U1 and an actual wave function that you would get other ways. You just go to Schrodinger equation, right? Our Schrodinger equation is hidden in the kinetic forms of the algebra. Okay, so as I say here, there is a normalization constant. If you want to have probability in the normal way, you would like this thing squared. That's the probability of being at position x, but I'm going to integrate over all x, and that's something you can easily do. The Gaussian has a nice closed form expression for its integral. And so what we get here is 1 has to be that Gaussian thing divided by a constant squared. So the constant is kind of ugly. It's the 4th root of pi h bar over m omega. I'm keeping all the constants, m and omega, here for the time being, just to make sure you sort of have to get your nose rubbed in that stuff, and then you put that away. You can make all that stuff equal to 1. So it doesn't bother us as much algebraically. Well, first excited state. And the idea is, and this is overdrawn here, what I'm not going up to the top of the screen here, I'm really going to go to there. That's what this creation offers. But high hopes, it has high hopes of getting, much more energy. We're already talking about really small energy here, so high hopes are embedded. This is the thick pen that's used to sign all of our presidential decrees now. So the first excited wave function will be one creation operator away from the vacuum. And that will be written this way, and this is the standard Schrodinger notation for Dirac's elegant wave function notation, where you have the coordinates on the left and the designation of the energy state on the right, the ket bra, or bra ket. And the creation operator needs to be expanded, okay, so that we can actually look at what we'll be dealing with here, and then we need to take the derivative of the function that we had, the Gaussian function, and then subtract that from the coordinate x times that Gaussian. So we have a little bit of calculus to do here, differentiation to do here, but the differentiation of the Gaussian kind of leaves the Gaussian alone. It just produces another x right here. So it's a question of this constant and that constant, and the h-bars cancel, so it's really, and we divide by a square root of MO we get here, so we really just get one term out of this thing. It's now m omega h bar 3/4 fourth. We get an extra value, an extra bit of that m omega over h bar, and this is the result. So it's x times the Gaussian, same Gaussian, okay? So that's what's shown on this other animation. This is next to the ground state vacuum. So the vacuum is there vibrating, and now I give it a little extra energy to produce, and let me get out of the way of the camera here. If I can get this thing going right here, I will just simply resume, and it should start going. So you can see it's noticeably faster. Okay? So that is nice. That's just basically x times the wave function on the right. Okay?
Dr. Harter?
And it's going around at the frequency that is assigned to it.
So to generate all these animations, what was your starting equation? Like, which equation did you start with to reveal all this?
This wasn't done that way. As I mentioned before, this is a real piece of fakery, but it tells you some physics. Basically what I do is I assign each point, in this case there's only 24 points there, I think. We can make it more to make this thing smoother, but this is quite sufficient. Each one of these points has a frequency associated with it. The frequency is determined by the potential. So as you go further and further to the right or to the left, you get into higher and higher frequency regions. That little guy there, if you hit it, it's going to oscillate at really high frequency, and the next one is really high but a little lower, the next one a little bit lower, next one a little bit lower. That's all this is. And then all I do is ask what happens when I put some function in there, and that function you can literally, with this program, you can go there and you can mess with these things. You can go in there and grab one of these things and add to it. As soon as you do that, you get a crazy mess, okay? So this is a real live program if you take it out of the region where we are. So let me just go start this again. This is the one I know and love, where only one phasor is moving. I can give it any amplitude I want, really. And it's just going to go and do that frequency. And they're the phasors that actually represent the phase of the oscillations of each of these harmonic oscillators. Just a line of harmonic oscillators that have a frequency determined by the potential. That's the way to think about quantum mechanics. Does that help at all?
I was just
So if I were an electron or something like that, and I am like in a, I don't know, maybe the fifth excited state, if somebody gives me a kick, I will just be really, really mad. That's the way I interpret.
Yeah. We're going to get to that.
Being really, really mad means higher frequency.
Yeah.
We're
going to do that. We're going to do boosts and kicks to this oscillator system. That's what you get to do when you play by this game, because you're really making a very cheap model of nature here.
Makes sense. It makes a lot of sense.
Really a cheap model. Okay.
But so, I mean, we have gone over that in my quantum mechanics classes, and that is, so there is the probability
Amplitude.
Probability amplitude.
Right. Psi.
Of getting out of the potential.
Yeah.
So
Well,
that-
it's each one of those points. Each one of these guys here has a certain altitude, right? Here, and the curve that's resulting from summing up of those, you know, is actually a jerky curve. I mean, you can see it's a little flat there because there's, you know, only a short distance between these guys. But the thing that you said, that this is the probability amplitude, each one of the points on there is the amplitude to be there. The
So
probability amplitude to be there. I mean, that is very strange language, right? That's what Feynman argues very forcefully, ways to get around that. But that's what a wave function is.
So
Psi of x is the probability amplitude to be there, literally the amplitude of the wave. Now, you have an absolute square of that.
Is 1 over the
That's the probability that you're going to get a charged couple oscillator to light up and take all the energy of some light that's been shined on this thing at that particular point. Which is, you know, as we were discussing at the beginning of class, an extremely magical thing. That all of a wave that comes in goes into one CCD. And then the next time it goes into that CCD. And it looks random. And it looks random because it's coming from something that's giving us random phases. And the thing that the CCD has also got essentially random phases. Now the game would be to get those phases and those to always talking to each other, right? You play it behind the scenes and make that, well, I can make it always go to this CCD. Maybe I could do that. I'd be turning knobs over here to make it go to another one. Okay? But we don't have any way to control all of the phases associated with complex CCD. Oh, we can't do it with a simple wave either. It does what it wants to do. Whatever that is. It's got a life of its own. So, I don't know if that answers your question about what we're actually writing right here for the vacuum. We're writing right here. This is a vacuum. It is not true. There's no light.
But, like, to me, it seems...
This is the absolute zero temperature light cavity. That's what it looks like.
So, like, that amplitude, like, I mean, what I can read from the graph is, like, you can find the particle, or the wave, should I say, out of the well. And if it is an infinite prism, as you said, there is no way to escape.
Oh, infinite.
Well.
Yeah, if you, like we were talking about the prison with infinite walls.
Mm-hmm.
Yeah.
How come does the particle wave, should I say, manage to escape that?
Well, this wave is, in principle, not zero anywhere in the universe.
So you can.
I mean, it just happens to have a curvature that's exponentially decreasing. So, you know, out here it's really, really, really small. And here it's really, 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 really small, and so on, right? But nowhere in the entire universe, according to this theory, is that amplitude ever zero, in a mathematician's sense. Because the mathematician knows the exponential never goes to zero.
Yeah.
Right?
Mm-hmm.
But you're bankrupt pretty soon, right? You're, you know, if you say you're bankrupt at 5%, well, you only have to go out here 3 units. E to the minus 3 is 5%.
Very low probability of finding that wave out of
0.05. Right?
What if it's canceling with another electron?
Well, we'll get to two things soon enough.
Then it can be zero
Yeah.
somewhere in the universe.
Well, this one is absolutely zero right there. So there's an example. You don't have to get 2 electrons. You can just go to the next excited state, right? It's got a node. But nowhere else is it 0. Okay? I mean, if we're going to play the rules here, them's the rules. So mathematics is really nice in the sense that it gives you very clean answers. But then you think about what those answers are telling you, and out here it's garbage. Right? But in our little model, you're okay. And by the way, that model wraps around. That's the only way to make it really work. So I show that up here. This point on this left-hand side is exactly the same as the point on the right-hand side. And that's why when you start really cranking this thing up, you see the thing's going around the ring. That's a ring. The simulation is a ring. Okay?
That well is infinite.
Yeah. Okay. Let's go ahead on this one. Get caught up here because I want to compare the algebra that we're doing this with. Now, we have the ground state well defined here, giving us a Gaussian, and then after the Gaussian comes this guy. And there is the actual wave function written out. And we're talking about the possibility of light with a certain frequency, that frequency this oscillator likes, making a very high probability, and this is something we have to derive later on, but this is a transition. It would be a transition from this to this. We can say a little bit about how, what happens when the transition occurs. And that is something we need to do in just a little bit. But what I want to do is a little bookkeeping. We've got to keep this going here with some bookkeeping. One of the things that comes up in, this is the beginnings of quantum field theory here, if we're talking about electromagnetic amplitudes, as opposed to some weird particle that lives in a potential well, electromagnetism makes its own potential well. And if you do that, you have quantum fields that have to obey certain rules to keep your bookkeeping under control. So we have a definition called normal ordering, where if I have some function of a's here, some polynomial of destruction operators, and then I've got another function that's made out of creation operators, and I'll indicate the creators by blue or green colors, and the destruction operators by red, kind of like the political colors that are now vogue for our politics. And indeed, the red is very much a part of the Chinese and Russian, the communist things were red flags, they're called red, right? And so I'm kind of using that here as a mnemonic for what it is we want to do. And the basic idea is that we need to evaluate a couple of these commutators. We're really talking about polynomials of both of those things. And the basic idea is to get it so the A operators are to the right of the creators. Okay, so the creators are going to be over here on the left. The red guys, they're going to be on the right. So that fits the mnemonic of politics is at work here. Okay, so the reason we want to do that is because we're going to be taking vacuum matrix elements a lot. And so if I can do that, if I can get this creator away from the zero and put him on this side, that means that when he hits this, he's going to give 0, and then this guy's going to be on this side, and he's going to give 0. So I'm going to be able to get a polynomial equal to 0, and then I can evaluate pieces of that in ways that you're going to see. So that's kind of the modus operandi for creation-destruction operator algebra. And here's something you should notice right away, is if you do A commute A dagger squared, you get 2 times A dagger. If you do it with A dagger cubed, you get 3 times a square of A dagger, and so on. I call this the power law derivative-like relation. Okay, so these are interesting things that have a connection to calculus. And we need to do a few more of those identities. Here's another one, a commutator derivative identity. What I do here is I say A comma BC. It's as though I'm kind of taking the derivative of BC, product with A. So I get an A with B, C left out, and then A with C, B left out, but left out so that it doesn't have to cross the C. Okay, so that's a relationship that's worth keeping in mind. Or this one right here, the same thing. These are all relations that are just true of any operator, and then we can make use of them to do expansions of the creation and destruction operators. For example, this one, definitely not normal order. I want to get the A creators over on the left and the destructors over on the right. So I'm making progress here by getting the destructor over there. Of course, I have this thing left. There's nothing more I can do with it, so it's the one that's going to give me the answers to some expectation value that I'll have to take here. And the same with A squared, A to the nth. Well, to make a long story short, as I keep raising, keep putting more and more destructors on the left and asking them to get over onto the right, and that's the idea of these expansions. There I've got 3 destructors on the right. That's where they belong, and I call that a normal ordering, and that is the idea of having, in this case, A cubed, A dagger to the nth. It gives me a binomial expansion with, in this case, a power law 3, so there's the binomial coefficients associated with 3. These are the binomial coefficients in a nice Pascal triangle, and so we're looking at these values right here. So that is an example of an expansion using these things. This is the bookkeeping that we like to use for these things. So in general, you will have a relation like this. A to the nth, and then A dagger to the nth. This will give me an expansion that is just a collection, a sum of things that are in normal order. That is, have the destructors completely moved over into the right, and then the creators are over here where they can be evaluated. They can produce something for us. Now, this is one where the powers are equal, and that's the only one we're going to use today. So this is a lot of stuff that we don't really need for today, but I do need this one. This is one that will give us generalized normalization for our calculations. So this is the one that we need to evaluate, you see. We need to figure out what is the norm of these crazy states that we make by doing lots of creation on the vacuum. If you do n creations on the vacuum, you're going to get an excited state that has some normalization, some constant, some amplitude. And we have to figure out what that amplitude is. And so we're all set up to do it right there if we use the expansion, okay? Because this thing right here is just this, and this is the only term that's going to survive when I take a matrix element using the vacuum, because this is killed by the vacuum, this is killing the vacuum, and so on. They're all in normal order. Only this one is left, you see. And so that's the tricky bookkeeping that we're doing here. We're getting that 1 is equal to n factorial, it's this thing here, over the constant squared. So our normalization constant is going to be the square root of n, factorial. Okay? That's the root factorial normalization that we need. So all that bookkeeping really, it's good for doing some other things, but today it's all we need. Okay? Is this making sense?
Can you go back one slide?
Do which stuff?
Put it on this one.
Yeah, can you go forward on this up to the previous slide than that one?
The one that came just before this.
No, after that.
Oh,
Previous
after.
to that one?
Do you mean
Alice?
after?
Yeah. Keep going.
Keep going.
The one with the monster equations.
Oh, the monster equation. Yeah, that's this guy
Yeah, that one.
right here. Yeah, this is m power here, n power here. But then the special case of that is the next page, right? That's where you had, and now it's all written on the chalk tray, but that's this. Okay? So everything in there is normal order, just like the doctor ordered. And we only use that first term. Okay? Does that make sense to what you were
Yeah.
after? Okay. So this is the big result. I mean, that's kind of neat. These great big waves we're going to be making with high N, the normalization
But
is
that
going to
really-
be huge.
But that really reminds me, if I were like in any other state or anything, so that equation right there, I mean, mathematically it just makes sense, but it's just like if I were normalizing the operator itself. Like if I apply the operator one over and over and over again, I'm normalizing the
Well,
operator.
that's
like
what is happening. To
Uh-huh.
make the end state, I have to go do this thing, not just once. We were lucky when he did it once, we got the right normalization automatically. Right? 1 factorial, 1, right? 0 factorial, what's that?
that. 1.
1. It's the first two states, we don't need this crap, right? It's the second state after that we need it, right? And we might as well put that guy up here while we're at it, okay? I'll just go over here, zero this guy out, and it'll probably blow a fuse. But instead of hitting this one, I'm going to hit this one. He's really going, okay? He's 2.5 times the vacuum. Okay? He's going 2.5 times the vacuum. And of course that motion is just his heartbeat. You can't see that. As soon as you go in there to measure that thing, you're going to disturb it and make a bunch of the other sons get all excited and just raise all ruckus and hell. And everything's going all over the place, right? Measurement theory, measurement theory. You don't have a theory for measurement. Okay? The collision of two very squirrely, oscillating, wiggly, fidgety worlds comes and just touches each other, and it becomes even more fidgety. Because you have beats going on between all of the frequencies, with all of the frequencies. So, you know, waves are so nice when they're just by themselves in one state, and we can think we understand, but boy, we really don't. Okay? So, I go and I apply a creation operator to the state. So say I want to raise this one more. Or maybe I want to lower it more. I'm getting tired of having these things so weak. I'm going to lower this. What happens if I do an A on that? That's why we really needed that normalization. Okay? Because what I can do then is I can say, okay, I got square root of n plus 1 here. I'm going to call this square root of n plus 1 factorial. This is n plus 1 right here. So this is the state ket n plus 1. Same thing with the other side there. Okay? So let me push the right button here. Okay? When I apply this, I got to do a little commutation to get this thing in the normal order. So that's out of here, and I'm left with this. Okay, so I get an n over n factorial, that's n minus 1, down in the denominator there, square root of n times n minus 1 factorial. This is the state, ket n minus 1. And here's the coefficient that I get when I apply that destruction operator to reduce this. And this is what I get when I apply the creation operator once. I get this, and then I get an extra factor on this. So you see why it's really important to have the normalization in order to do this algebra, right? You think, oh, I don't care. I'll normalize, schmormalize. I'll just do it every time I make a new state, right? No, you don't want to do that. That would be really troublesome. But this is really cool, okay? Now, Feynman's mnemonic rule, larger of the two commutators goes into the radical factor, okay? N is larger than n minus 1, so in it goes. Here, n plus 1 is larger than n, so there's where it's the one that goes in the radical factor. You know, mnemonics don't hurt. If you've got a photographic memory, you're probably going to be terrible at physics. That seems to be a rule. But if you have a terrible memory, I don't know if the thing says that you're going to be a great physicist, but Feynman loved mnemonics because his memory wasn't all he wanted. He happened to have a very good memory, but he wanted more. Anyway, the idea here is the case where A dagger A is not quite equal to A dagger. That's kind of what we're always saying about these operators. You see, here is the A dagger, okay, and you'll notice that there's an extra 0 row in it, right? Whereas this one has an extra 0 column. So this is a situation where if I put it this way, I don't get quite the same thing as if I make a product going the other way. This is a counterexample to the unitarity. These things are not unitary operators, but they're almost unitary. Okay? Anyway, welcome to infinite dimensional quantum space, because this goes forever this way and has that problem that normally you wouldn't be too worried about. Okay, let's catch up here and see if there's anything I could add to this. Number operator, Hamiltonian operator, that's something we need to do. Okay, so let's get busy with that. This, I think, is really important, the Hamiltonian and the number operator. This thing right here counts quanta, and that's I think, an important idea. We're going to use our little expansion again here, and that gives me, this is the only thing that's surviving there, so I get an A dagger in on a vacuum. That means that when I apply this operator to this state, I get a coefficient that is the quantum number of the thing. If I can, of course, I'll take the expectation value of that. But this is the Hamiltonian. Hamiltonian is A dagger A. So all it's going to do is give us n plus a half for a one-dimensional oscillator. Or for a two-dimensional oscillator, n plus 1, 2 of these halves, and so forth. Okay, that will be next lecture to deal with that. So here is the matrix representation of A dagger A, the product of A dagger and A, okay? It comes together rather nicely with a 0 here and then the quantum number, but don't forget the halves. They show up on the diagonal too. So that, I think, is enough about our bookkeeping. We can start to do some things. Now, we also need the expectation values of position, momentum, and then the uncertainty of both of those things. That's what's coming next here. And this is what's so easy. You don't have to do integrals anymore. Every matrix element you need is now available using the normal ordering, shall we say, formalism. That's a very strict bunch of group theoretical, really algebraic rules. So here's the operator for position, x, A plus A dagger over 2, just from the definitions of A equal x minus IP and A dagger equal x plus IP. Add those guys up and you get x. Subtract them and you get I times P. Divide by I and you get P. Okay, so if you want expectation value of momentum, to any power, you just take this thing to that power. If you want an expectation value of this to any power, you take this to that particular power, in this case a power of 1. So what you find is, and this is no big surprise, is the expectation value for position is a big fat 0. And that's what you're seeing with those waves there. Is there's just as much plus as minus on either side of the middle of the potential. And it's a probability, so it doesn't care what the phase is. The result is everything is centered in a harmonic oscillator. So I get absolutely no value for x or the velocity. Also, the momentum is equally positive and negative. 0 is the expectation. But these guys are not 0. This thing does not come out to be 0. This comes out to be quite a bit of a mess at first, but when you use your normal order effect and get all of the destructive operators to the right, you end up with just 2n plus 1 for both of these, and then a constant. And that's why I kept those constants, because you can see these are very different units, so they have to have different coefficients. And then uncertainty. How much slop is there to a harmonic oscillator wave as a function of quantum number? That's really important. That's something that really is the key thing to doing measurements with electromagnetic fields, which we have two world experts of that, Surin Singh and Rita Vyas, his wife, both do some really excellent work in photon counting, which you know about, certainly. And you've probably talked a little bit.
Photon counting.
Yeah, and I don't know if Al has spent much time with the noise factory, but it's really interesting stuff. Anyway, the actual delta x, that's the average of the difference from the mean squared, root mean squared, that's really what we're after here. That thing works out to be here, this thing. This is the root mean square. It works out to be square root of 2n plus 1 over 2 with the that one down there, very similar with the both. So the uncertainty, that is the delta x, the square root of the root mean square of both of those things, comes out to be that. And this is really a beautiful result. This is one-dimensional oscillator in state n, okay? Gives you that width. And it goes up linearly. That's kind of weird. Because the parabola, doesn't it go up quadratically? This is kind of strange. This is really quite an amusing thing, actually. Okay. Now this is the minimum uncertainty product. If I go to the ground state, the vacuum, the skinniest that wave can be is h bar over 2. That's with a frequency omega added, multiplied there, the vacuum value of 0 point. Now let's just stop for a moment. I wanted to sober us up a little bit. We're so good at making these. I could go and apply my creation operator 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 18, 19, 20 times, and I can make a wave, right? And this is actually one that's, I crank up the number of phasors I have from 24 to, I think I had about 100 or so phasors in order to do this one. Okay, look at all the dots there, okay? That's what I got. And that's really cool. That's kind of cool. And not only that, but there's a curve that cuts through here. A curve that you should know about. Arc cosine. Isn't that neat? That arc cosine fits this thing in the classical turning point. The classical turning point for this thing is right where the wave function evanescence right there, okay? But we're talking about this energy, so it's right here and here. That goes up, and those are the asymptotes of arc cosine, okay? That word? Now what is that? see the shadow of my hand? You can see my hand's right here, but what if it is a wiggly hand? Where do you see a really dark image? Here and here, right? But not in between. So you see it very high on the ends here, right? Very low in between. And it's more emphasized if I do the arc cosine squared. This is the actual amplitude, right? This is psi. Do psi star psi, it's even more noticeable, arc cosine squared. So that's what you're really seeing classically. This thing is oscillating. Pretty good. I'm a pretty good harmonic oscillator, right? They don't pay me enough for this. Okay? Isn't that cool? I think that's worth noting. Now, the n equal 20 wave is a long way from a classical energy. Say you wanted to get 1 joule of energy in your oscillator. That isn't much, right? Newton's a quarter of a pound, right? Okay, and then you push that quarter pound over a meter. That's not very much energy, right? But how many quanta is it? 1 joule at 1 hertz. Let's just have a really slow oscillator, okay? 1 joule at 1 hertz would take a quantum number of 10 to the 35th. 1 joule! Now you've got to know this stuff. You've got to know what you're dealing with here. You're dealing with enormous numbers. Enormously large, enormously small. Depends on whether they're in the numerator or denominator, right? And all of them are one of those two places. How long do you think it's going to be before I get a computer that could completely analyze the quantum mechanics of a 1 joule oscillator? I can be able to handle all those digits? Just for one thing? Forget about it, as they say in New York. Forget about it. We got to be smarter than that. But this is not going to happen, right? But it's happening all around us. Everything we do has got more zeros on it than that when you're talking about quanta.
Dr. Harter, so how did you find out that the envelope magnitude would be arc cosine? Like, did you just try to look at the shape?
I just did this. I said, of course. This is a cosine, right? What's the probability it'd be here, 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 and here, right? That's why it's arc cosine. It's really simple. Isn't that right?
You solved a simple problem.
Yeah, it's a, you know, forget the scale factors, right? The form of the function, right? Pretty neat. So worth contemplating. It's not a, I mean, it's a glib answer I'm giving you, right? And I'm not the one who discovered this. I think Feynman mentioned this once too. And yeah.
You could see some qualitative evidence in the center. The frequency is much higher than
Of course, yes.
the frequency on the ends.
Yes. As you approach the classical turning point, it stops completely, right? But out here, you're starting, you're seeing the K value of this wave, right? And there's the highest K value, right? Thanks for noticing that, right? But once you get going, you see, you disappear, your shadow disappears, right? It gets very small and intense, in darkness, right? This is a measure of darkness. Okay, we've got some interesting stuff to do. We've still got about a half hour. I want to do some more animations. The dynamics of mixed states. And every one of these different states has a different frequency. It's just a quantum number times omega, times omega, no h bar, and h bar gives you the energy. This is the sum right here of something that's going at a frequency omega with something that's going at a frequency omega over 2. Okay? Well, this one is really going at frequency omega plus a half, and this one's going at just omega over 2, okay? I'm sorry, 1/2 omega. So this one right here has the speed of the 0 point motion, which I will set up on the far screen there. Actually, I should do this when I'm going to do the far screen. Just out of the way here. Okay, to the right mouse. First of all, 0 this guy, and start up our vacuum. Okay, I'll give it a phasor that's, you know, a little bit bigger than the box. Catch the corners of the phasor box. Okay, and then I'm going to add some excited state. Okay, shucking and jiving there, right? This is a little dance, okay? And that's what you get. That's what you get when you look at the probability distribution, but even if you just look at the wave function, you can see I've got 2 different frequencies here. This guy here and this guy here, and I make the product of them to get psi star psi. That's your probability. I'm going to take the square root of that. This will be the magnitude of the wave as a function of space and time. And all the time behavior is going to be on the cross term between the psi 0 and the psi 1. Okay? Psi 0 is just a Gaussian, and psi 1 is just x times a Gaussian. Gauss and ungauss in. So the product of those two multiplying this thing and this thing is going to be a cosine of the difference in frequencies. So what we're talking about is a beat frequency between the ground frequency and the excited frequency. And that's the only motion in that thing. All of the time behavior there is this. There's one Fourier component, and that's it. The difference between the two energy levels. This isn't moving, this isn't moving. But this is if I have some place where there's overlap. And boy, we've got lots of places with an oscillator. They're right on top of each other. So this is very healthy. But you should be aware, this is kind of what it looks like. I'm not trying to make a phasor to follow it. We'll do a better job of that in a little bit here. But right now, I'm just dealing with the frequency of that phasor. And I'm just sort of picturing it and going around in the usual clockwise way. But we do need, in order to have any wiggle, overlap somewhere, or it won't wiggle. In other words, if I have a wave function, an eigenfunction that has a wave down here, and then it tails off to practically nothing, and then another eigenfunction that's down here, some lump, it tails off to practically nothing. So this one is sitting on the nothing of that one, and this one over here is overlapping the nothing of the first one, okay? Then nowhere on X do I have any overlap. So I will not see a beat, no matter what the energy of this is or what the energy of this is. That system isn't going to move noticeably. Okay? So you're not going to get this beat effect unless the wave functions have some part that overlaps with some part of the other. So this product doesn't get zero. That's really important. For measurement theory. You do a non sequitur. Okay, so the beat frequency, first of all, the lessons here. Beat frequency, always a difference. If you're just talking about two levels doing a beat. Now what happens if you have not just two, but three? If you have three things that are going with different frequencies. Turn my hand like this, okay? Now you've got a beat between this one and this one, a beat between this one and this one, and between this one. So now you have three beats going. Assuming there's the overlap, that they all overlap with each other. Okay? What about 4? What about 5? You're starting to get a lot of beats, right? n times n minus 1 over 2. We're talking about triangle numbers here. Okay? That's how many beats you got.
So, so here basically what you have is a superposition of two different oscillator states oscillating with at different frequencies.
That all the oscillator states do oscillate at different frequencies for one dimension. Not for 2 or 3, but for 1. Absolutely true, right? If I'm a different state, I'm going different speed. Right? Because the frequency is h bar omega. That's
right.
plus 1/2, right?
That's right, yeah. That's it.
Right? N h bar omega plus 1/2. 0 point, right? H bar omega. N plus 1/2. So, yeah, you change the n, you change it by 1, you get a beat of 1. So this omega here doesn't have the 0 point in it, right? You'd never measure the 0 point. You'd look in the spectra of this thing. And remember, that is really the idea here, is that you can't measure the individual frequencies. When the thing's in an eigenstate, it's dead. No matter what eigenstates it's dead. Unless it can couple with the electromagnetic vacuum, which most oscillators can do. But if it's an oscillator that doesn't have any charge, it's going to be a dead duck. It's not coming down. Whereas if it's up here in a vacuum and it's got charge that it's oscillating back and forth like that, that's an antenna, right? That's an antenna broadcasting at some rate. So that, to make this thing realistic with the outside laboratory, that should be shrinking exponentially, right? That oscillation. Until finally end up in the vacuum with just the Gaussian going blah, 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 blah. And that's dead. That's dead, right? The probability of that has no time dependence at all. So this is how quantum mechanics stays alive. It's by mixing. Okay. The transition frequency is the transition energy. I mean, this is Planck's rule. Frequency is energy, energy is frequency. Phase frequency is what it really is. Frequency of a radiating antenna, transmitter or receiver, depending on what the phases are between it and some absorber outside, which will take the energy and throw it away, not give it back to you. And of course, the most interesting experiments are when it does give it back to you. Breaks this Fermi golden rule. Okay, now we've got a little bit of time here. I'm going to rush through this pretty fast. It's something that you really, if you don't know it already, it's worth studying. This is where I go up to an oscillator and, kind of like any kid that's in a museum and there's a pendulum or something there, right? Or something on a spring, right? What's the thing you want to do, right? Whap that sucker, right? Right? Well, if you're a more calm and shall we say, mannered youngster, okay, you pull it over to the side, right? Let it go. That's more, I think, civilized than going up and punching it, right? It's more just go over and let it go, right? Right? You'll do the same thing. It's a harmonic oscillator, okay? So that's what we got here. We've got translation, which is going to be done to make the wave function move a distance a. Or we've got the ill-mannered child who's going to boost it. He's going to punch it, give the momentum a boost. Okay? So we got to figure out what those operators are to do that. Because this is what's going to make the coherent state. These are the operators going to produce coherent state, which is very important. Lasers operate with coherent states. Huge numbers of so-called photons, huge numbers of N, all mixed together. All mixed together. You'd think it'd be a mess. It's not. It's beautiful. Or we wouldn't even be talking about it. Okay, so That's what we need to do. We need to shove it, A units, okay, some way that I can apply an operator to a bra and make it go to x minus a. Or I got to do T dagger A on x and make it go to x minus a. So a little bit of bookkeeping here to get the right sign on the translation and on the boost for the momentum states. If we're talking about a plane wave that has a very sharp momentum, this operator is going to be something that we want to look at. Okay, so that is the deal. We need to get that going. And these have names. I'm going to speed this guy up here so that we come out more or less in line with each other here. So, what we do is we say that a very small, infinitesimally small, say, a translation is just the identity operator plus linear amounts of something called a generator. Okay? And the generator is just a derivative with respect to A. So this is just the first term in a Taylor series. Well, it's first term in a Taylor series, it's going to make an exponential, actually, if this is a constant. But you don't need to know that at this point. We can just say, oh, that's my operator there. I'm very happy with that. And this one right here, it's the same deal. Okay? So the two things are going to have, we have to calculate and see what it is that you really would have here. Now here's the interest formula, okay? Compounding at a certain rate, n times. The rate gives you 1/n each period, okay? So this thing is well known as the exponential. So that's really what we're doing here. We're going to do a finite boost by applying an exponential g. We have to figure out what g is now. We're kind of, it's the derivative here, but we'd like a better expression for it, and we'll get that in a bit here. But e to the a times g is written a little small there. This one is e to the b times, and this is the k generator of boosts right here, also exponential. Okay, so this is the where the bookkeeping gets funny. Now, with this g being a derivative like that, I find that when I work on a function of x, what I'm really talking about is e to the minus a partial with respect to x. This is the way I get a Taylor series for describing a wave function that has been translated by a certain amount. And it is a power series that goes on forever, but it gets increasingly reduced if you don't copy and paste 2 factorial where it should be a 3 factorial. Worth getting that little typo out of there, but that's basically the idea. So the g has a relationship then with this. It's minus IH partial with respect to x, so g is minus I over h bar times momentum. That is minus the partial with respect to x. And this one is minus the partial with respect to momentum. Or if you want to let momentum be h bar k, it's a derivative with respect to the wave vector of the Fourier components. Okay? So, let's keep this thing going here. Finally, we get at the very bottom there an expression for the effect of the boost and the translation. Now, the bottom line here, as I say, and I'm saying move this up so that you can read it, and that's what I'll do over there on that. Well, I can do it here too. I'll leave that screen there and just move this all up here so you can see. Check the translation operator on a plane wave, e to the I kx. How does the translation operator that I've just given you here work? That's this one. Work on e to the I kx. Okay. Well, e to the minus I a p over h bar times e to the I kx. Well, this is a derivative right here, so it's a function that gives me a times k. A times b gives me a times k, and the h bars cancel. Okay, so that becomes e to the I wave function k x minus a. That's a wave function that has been moved positively if the x here has been something subtracted from it. The x position has had something subtracted. Correct. bottom line checks. This one, I do these thing here. I do e to the bx now here on this. And so that's e to the I bx over h bar. K, well, what I get here is k b over h bar x. That is what this one gives us. And let's see if that's right. That's a boost in the k. Without the h bar, k over h bar, that's back to the momentum. Momentum p is h bar k, okay, for this one. So that's a little bit, and this is the same k being used as a victim on either side. So that's just to check all of this crazy algebra actually works for every plane wave, and then every function is made out of a plane wave. So that's good. Okay, now here's where it gets really squirrely, and I'm going to really rush through this here. You can come back to this later on if it's necessary. But these operators don't commute. So the question is, which should come first? Is it a matter of taste? And that's pretty much right. It's a matter of taste. The translation, should that be the thing you use and don't even bother with a boost? Or if you're going to do both of them at once, which one should be first? That is an answer that you can probably say neither and both, but we're going to go ahead and combine them all at once in the exponential. Okay, now where is this? There's something we've done already that's like this. This right here, where you do all the combination in the exponent, is what we've got here when we did the Darboux rotations with the crank. The crank had 3 components, right? And they multiplied a generator J, angular momentum. Okay? Whereas when we did Euler rotation, we had 3 factors. First we did gamma with a z, then we did beta with a y, and then we came back with a z again to do alpha, the final dial setting of the azimuth, right? So this right here would be like stacking these things up. Here they're all in the exponent, like what we've drawn here. And this is what's often used. So it's worth mentioning it when you discuss coherent states. Now, we can evaluate either one of these, but there's this weird identity. As I say, I leave this as an exercise because when we do it with x and p, the fact that the commutator of x and p commutes with both x and p lets me use this obscure but important relationship involving exponential operators. And so I go ahead and just use it to write what this exponential comes out to be, where I've got them all combined in the exponent. So it only makes a difference. If I do the boost after I've done the translation, then I have a minus IAB, product of those two distances. If I do the boost first and the translation later, then I get this phase factor. So the phase factor is going to be e to the IAB in units of inverse h bar. That's all it makes. That's all that's going to happen if I do these things in a different order. So why worry about it? But the fact is, we want to get everything right. Remember, we've got somebody in here that's got professional information science, and they're going to have to worry about the phase, right? Once again, we better get this right, okay, if we're going to use it. Okay, so we'll go ahead here and we write all that out. This is the coherent wave packet state done by boosting and translating. This translates, that boosts. And we get a thing like this. It has some phases of creation and destruction operator. Well, the destruction operator is immediately zeroed out. So all I get is an exponential of a creation operator. That's cool, okay? I can deal with that. That is something that makes a lot of sense. It's just an expansion in power of the creation operator, and that means that we're going to have a coherent state made as a linear combination of n states, and we've got to divide by n factorial to keep the normalization from. And then outside is going to be a Gaussian that has the alpha 0, that is the magnitude. of this alpha parameter that I'm putting up here. Now, the alpha parameter is just the real and imaginary part of the phasor, a classical phasor. Remember how we would give a certain size to the real part and then divide by omega, and actually m omega if we're talking about an oscillator, for the velocity part of the phasor. So this is basically the whole thing written. Now, it's worthwhile that what we've done here is we've evaluated the time evolution operator. That is our exponential that we worked so hard on with the crazy thing theorem. We could have used that, but this is a much better way. This is the result that we're working with, or that we're going to work with. That's the actual coherent state doing its coherent thing. So let's get this thing up to speed here so we can look at that. So the time evolution simply determined, because all of the phases are harmonic. This is a system that's totally periodic. All of these phasors, from the very lowest one, for the very lowest vacuum phasor at the bottom, it's going at half of omega, to the very highest one that we might have in the consideration. And this isn't Gaussian, so we don't have to go very high before we stop worrying about it. Usually a 2, 3, 4 or something like that is enough to make a very healthy coherent state. Okay, and then it's exponential, Gaussian exponential, squared exponential die-off after that. Okay, so you're up there with something that's going 4 times as fast as the one that is the ground state. Okay, anyway, they're all related by integer, right? Each of the frequencies is related to the other one by a rational fraction. So at some point, the denominator of that fraction times the period, everybody comes back to 0 on their phasor. So it's a completely periodic system that you've got as an oscillator, no matter what you do to it. But the coherent state is really cool because it does what a classical oscillator does. The whole thing oscillates back and forth with this phasor variable here. This is the phasor coordinate, alpha, okay? Real part of the phasor, imaginary part of the phasor. And it's a circular phasor, you see. Just because P has an M in it that cancels that. And then this is the omega that just cancels the omega that comes from the derivative of the velocity gives. So we cancel that thing and we get a circular motion of this alpha. That's really important. It's our old friend because we've been doing with phasors here. So it mimics a classical oscillator oscillating around a circle, and it goes clockwise. That's the thing. It gets the top of the thing. That's a positive velocity. It's got to go this way. So it's got to go left-handed. It's got to go clockwise, and that's what we're going to see here. So this is a picture of what we're going to be simulating. Let's get it going. That thing down there is not a coherent state. It's just 2 states. But if you, and this is something I have to set up, I don't go in there and grab every phasor by just the right amount. I just click this button right here. And there she is. And you can see the phasors there. And to help you see that, I will increase the size of them. This doesn't affect the calculation other than the deposit while it changes the graphics. But there is a coherent state. Now look at what its energy is. It's just a little bit below that particular guy there. So the expectation value of the energy for this we have to calculate. And it looks like it's some weird value. It's not just 1/2 between the 2 levels. The thing about this, you see, is unlike what you always say about quantum mechanics, is that the quantum theory eliminates this any energy between the quantization energies, you see. And people sort of repeat this, say the state can't be in this energy. It can't be in an energy in between there. Yes, it can. This one is, and you can be anywhere in between. This is analog. I can make this thing have any energy I want it to have. And I will, just below that will be that half omega, that 0 point motion, okay? Subtract that. That's the actual classical energy of the oscillator that is being mimicked by this quantum mechanical system. So we've got a distribution here that you can see, this nth power of the alpha 0 divided by n factorial square root. That gives me what's called a Poisson distribution. It's just a Gaussian that's run into the wall. As I crank this thing up to higher and higher values without changing the width at all, I'll end up with pretty much a Gaussian distribution way up there, and then this will be very small. So that's our, I don't know what you want to call that thing, Schrodinger cat. It's kind of like a cat. It very sneakily moves along to jump on something and then moves back again, right? Jump on something. But it doesn't jump. I mean, look at how graceful it is. Goes up to the edge there, okay, and comes back. Where exactly does it turn around? It doesn't quite turn around where the peak is over the intersection of its energy. It turns around here, a little bit below. That's the classical turning point. That's where it turns around. That one's is almost stopped right there. Isn't that cool? So if nothing else today, I thought you ought to see the only quantum system I know of that essentially copies classical mechanics perfectly. And it does it in 2, 3, 4 dimensions too. This is just one dimension. Okay? Now, what is a trace? This program will also trace in 3D, but I won't waste time making you see that. First of all, let's go ahead and on both of these machines look at the expectation value of the destruction operator. Okay, turns out the destruction operator on a ket has an eigenvalue equal to the phasor. And presumably that phasor can be time dependent still if this works. A coherent bra state is an eigenvector of the creation. But the creation operator is not an eigen, this is not an eigenstate for the creation operator. And this is not an eigenstate for that. Okay, it gives you a mess each time you try that. But in between that you have these two